Hello everyone. Welcome to this presentation. This is Richard Ogwal, a member of the group Software Engineering ML44, and today we are presenting our project with a title Machine Learning Approach to Database Risk Prediction under Extreme Level Scarcity based on semi-supervised and positive and level learning. So in this project, we shall explore how artificial intelligence can help detect database early, even when we have very limited level data, which is common in a real world healthcare system. Without wasting time, let me dive into our presentation roadmap. That is, we shall move from the background and introduction to the final site, that is now acknowledgement. Coming to the background and introduction, diabetes is a serious global health challenge. Currently, over 537 million adults are living with diabetes, and this is the number that is expected to exceed up to 700 million by around 2045. So the majority of the problem is that the detection is difficult, especially in a low resource environment where access to tests like maybe HbA1c and blood glucose is limited. Because of this, many people remain undiagnosed until complications arise, such as heart disease or other blindness. So our work focuses on solving this gap using a machine learning, that is a technological uh, aspect of solution. Now coming to our problem statement. In many health care systems, especially in a low resource setting, um, patient data is incomplete, so we face three major challenges where patients have no labels, some have very few labels, and in some cases we only know positive cases. So this makes it difficult to train machine learning models. So the key problem is how we can accurately predict the database risk when most of the data is unlabeled. So that is the core objective of coming up with the solution. Um, so regarding that, we dive into a research question and objective where uh, our research is guided by the following question. Uh, can, can we build, can supervised learning identify patient subgroup linked to the database risk? And the associated objective that we want to achieve in that question is to perform exploratory data analysis with at least 25 visualization to understand future distribution, correlation, and class separability. Then, does, se- does semi-supervised learning perform does semi-supervised learning outperform a supervised baseline when only fractions of level are available? Then the associated objective we have is to implement and evaluate a supervised clustering algorithm, such as DBScan, hierarchy clustering, and also access their alignment with the true level data. Then, how effective is PU learning in detecting the hidden positive um, positive when all the positive cases are known? So we map it to objective is to implement and evaluate semi-supervised learning method. So those are some of the research question and the associative objective that is guiding our our workflow in coming up with appropriate solution in this um, approach. Then we move into our research methodology. So our approach combines three key machine learning strategies, that is supervised learning where no levels are available. So in this one, then also semi-supervised learning, then positive and level learning. So under this one, that is where we start by data loading, data pre-processing, that is cleaning, then ADA, modeling, evaluation, and interpretation. So all this methodology that I talked before started within this pipeline. Um, then coming to data description, in our dataset description, our dataset use include patient-related features such as symptom, age, gender, and also um, MBI that is now in a split protocol. Then, since many records do not confirm diagnosis, these datasets reflect the real label scarcity conditions. As we can also see from the variation under classes, we see like the positive level carries 60% and negative also 40%. So the total sample is 520. Then we come to uh, analysis inside it, that is now under univariance analysis. So we're trying to see now how this categorical variable, that is now in this one we are seeing age distribution and gender, that's now like patient. So we're trying to see the pattern of distribution within the patient, that is under age and also gender. So the analysis gives us the available inside of the data. Then coming also into bivariant analysis, we are seeing how the two categorical variable are distributed in this pattern. So we can see like from here we have weaknesses versus diabetes. So we can see now the clustering in between, and also the same applies to other variables here. So pair plotting, that is now for the most predictive features. So we can see from here how the patterns varies. Age distribution by gender. So age distribution by gender, actually now the analysis tells us within 30 to 60 years, that is now the gap where people are most likely to have uh, this risk to diabetes. So the distribution is clearly shown in the diagram, in the graph here. Then coming to unsupervised learning. Now in this unsupervised learning, we applied several clustering algorithms to group similar patterns, to group similar patterns rather. Then we use k-mean clustering, that is using a distance-based clustering, and then we also use the regression mixer model, that is now probabilistic clustering, and then we also use DBScan, which is used for detecting outliers in the analysis. Then hierarchical clustering, that is now for visualization of data structure. So this method helps us uncover the hidden pattern in unlabeled data. So coming to semi-supervised learning method, we use two key algorithms, that is label propagation and also label spreading. So this method works by binding graphs of data point, spreading the known level to similar unknown. Then this allows the model to learn from both level and unlevel data effectively. Um, so we jump up to the positive unlevel learning. So the goal of this learning is to detect an hidden positive when all the positive level are known. So in many real world cases, we only know uh, patients who are diabetics, but not those who are healthy. So The first step in the method, that is now the two-step PU learning, that is we identify the reliable negatives, retrain the model. Then coming up to the second method, we use multiple decision trees, train on different sample, and also combine. Sorry for that interfering. Then we combine prediction using voting. So the method is very powerful for detecting hidden diabetes cases. Then coming to evaluation of metrics. So because of detecting the hidden positives, many appears as false positive. So therefore, we focus on using evaluation metrics such as the pre-recall, the recall, that is sensitivity, then the true positive um, recovery rate. So this matrix better reflects the real world performance. So that is why in the screenshot we can see their levels and the method. We also some assumption we included while guiding uh, the matrix evaluation. Then under result, that is unsupervised learning. That's now we see the method used, that is k-mean. The CILO scores is 0.28. So in this performance, we can see like the DBS scan was able to have the highest score than the two clusters. So that was the brief overview of metric evaluation in unsupervised learning. So under results of semi-supervised learning, we can also see the semi-supervised learning outperform supervised learning at least 10% of level data. That is, at 10% of level data, semi-supervised learning scores 80%, 84%. Then supervised 73. And also at 30% level, we see like semi-supervised learning scores 91%. Then also supervised scored 86. So this proved that using unlevel data proved a performance significantly. Then now we come to PU learning. So our best performing model, PU bagging, achieved 92 accuracy and recovered 94% of hidden diabetic cases. So this is critical because early detection save life. So the strength of this method comes from handling noisy data, then using ensemble learning and avoid overfitting. Then coming to the comparative analysis, so the analysis of what I was talking about comes here. We come to edge deployment and execution. That is now the system is designed for the real world use. That is what I can say under deployment. That's under edge future. So we deploy the model as on the device AI as on device. We deploy the model as an on device AI. That's now like AI which is going to run on the end user's device. So it works by users entering the symptom, the model processes the data, and the system output risk probability, then display the risk band. Um, so this makes it ideal for low resource health setting. Then edge features, we can see like the system runs on entirely end user's device. That is what I have talked about. Then the patient data stays within the local device, so meaning the security is actually concerned. That is under privacy. So that one is about edge and edge execution. Then coming to knowledge distribution. Then we use techniques called knowledge distribution. That is where a large model trains similar model. That is now student, a teacher training a student. That's what I can say in shortcut. The smaller model is faster, uh, uses less memory, maintains similar accuracy. This is perfect for our edge devices where our end users are going to use. So this light model is the logistic regression, which is having a size of just 2 KB for a light deployment. Uh, that is now, this is a simple illustration of the teacher being a random forest and the student being the logistic regression model. Yeah, so we can see now the teacher is 63 times the larger, then also the student is just 1.4. Distillation, then the benefit, the size reduction, that is now the benefit of the distillation process we did, then accuracy retrain, then the FI score reserve, preserve, then deployment, that's now the lightweight model being a light one. Then coming to the limitation and ethnic, we can see now the limitation that we were having. Our dataset scope was just covering a few scope that is just within the diabetes, then also symptom encoding. We were just symptoms are encoded as binary, which simplifies the clinical readiness, but we are not capturing other symptom variables, maybe like such as symptom duration, intensity, and frequency. Then ethical deployment, that is earlier on before distillation, we're encountering that, but later on we 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 went to the light deployment. Then the recommendation. Where is it again? The recommendation. So our system can be used for early database screening. That is because we when only positive level available, so our PU learning can give us 96. So we recommend using the positive level data for the accuracy. So then semi-supervised learning, when we have few level data that's available at 30%, less than 30%, then no level will recommend use of unsupervised clustering for exploratory insight. Then all level data, we we recommend the use of supervised learning, that is the upper bound. Then the future work, in the future we plan to improve the model accuracy, and that is calibrating the model, and then expanding our data set to cover other diseases, and also integrate wearable devices. That is now we bring it under fairness and bias audit so that we can integrate inclusiveness in the system, the lightweight deployment, like further distillating uh, our, our current model so that we can have a light and a lighter one. Then the references, these are our references. And acknowledgement, we extend our gratitude to the core team members, that is Babira Sandra, Oscar Pio, and Richard Ogwal. Then our institutional affiliation, that is our academic guidance from Makera University, we acknowledge and support. We acknowledge for the support provided during this entire learning process. Right. Thank you so much for listening.